So, in the previous session we have discussed about the process design of different extraction liquid extraction processes, which includes the single stage, cross current and counter current, and additionally for the case of cross current as well as for counter current, we have discussed that how to determine the tower height and then the number of stages for these systems where the carrier and the solvent are immiscible to each other. So, see distillation, absorption, then humidification, they are all basically gas liquid contacting pattern or gas liquid contacts, right. And where in gas liquid contacts we have certain advantages. What are the advantages? The interfacial tension of a gas liquid interface is quite low compared to two liquid interfaces, and additionally there is a huge density difference. So, what happens because of that? For liquid extraction, we have two major operational difficulties. Number one, it is difficult to disperse one liquid phase into another relative to the process of dispersing a gas in a liquid stream, right. The reason is interfacial tension of liquid system is much higher than gas liquid systems, and as the interfacial tension or energy is much higher, we need higher mechanical energy, higher energy budget is necessary for LLX, right. The second operational difficulty, delta rho liquid is much lower than delta rho gas liquid, and because of that it is rather difficult to separate liquid dispersion into two pure phases. So, see, because of these difficulties, there are the consequences different types of LLX equipment, right. In the baseline type, we have the facility to disperse mechanical energy, which at the same time has got higher capital investment, and we cannot go for higher number of stages. So, that we actually upgrade in different other designs. Okay. So, liquid extraction equipments are like absorption and distillation equipment is still developing. Okay. So, different types of designs were proposed based on, and they have got their inbuilt advantages and disadvantages, inherent advantages and disadvantages relative to the other. So, first we will try to understand that because of these two difficulties, we have different varied designs, right. Some is actually reducing the capital investment, some this operating cost and some both, whereas some going for higher energy budget, but high efficiency of mass transfer, etc. Some are very compact design, but of low capacity. So, it is not a universal one or two types of designs available, it is a multiple varied wide spectrum designs of different types of LLX equipments are there. So, we will try to understand the basic classification. Classification of LLX equipment. First, based on mechanical or based on agitation. So, you can have definitely unagitated column. Unagitated systems which incorporates spray column, packed column, next this sieve plate column. Just like distillation or plate column we have studied in absorption tower. Next, pulsating system. Here we can use plate or packed column with external pulsation generating accessory. Third one is mechanically agitated columns. Here we can use rotary equipments where there is a starter and a shaft, or we can use reciprocating equipments. Rotary devices, a rotary column, or rather exactly rotary agitated contactors. And reciprocating columns. This is reciprocating plate column, car column. Next, here we have this Seibel, SCIEBL. These are different designs. Seibel column, RDC, which stands for rotating disc contactor. It was developed by Shell Corporation in 1952. Next, old shoe Rushton column, then Cooney column, etc. Right. Whereas instead of agitation, we can use this centrifugal force field to actually create the phase contact, right. Use of centrifugal force field to generate or to facilitate phase contacts, that is pod extractor, the most popular. Used for what I have discussed, the penicillin extraction, we have this pod extractor, and there are other variations as well, right. So, this is in general the classification of the different devices in liquid extraction. Now, we will discuss about the very basic idea of this equipment and the respective advantages and disadvantages. I will not go into the detail of their construction, but a very basic idea regarding the utility of this equipment, right, advantage and disadvantage, and where they have got their use. The first one, you see, mixer settler, right. So, mixer settler, as we have discussed, we have a mixing tank where we have the feed and the solvent. So, this is the mixer, and next it goes to a horizontal type unit with baffles and exit for light liquid and heavy liquid. So, light liquid out, heavy liquid out. LL stands for light liquid, HL stands for heavy liquid. So, this is simply a unit, right, equivalent to a single stage. So, this has got the features high stage efficiency, as you can understand. It attains nearly the equilibrium condition, right. They can handle wide variety of liquids with different volume fraction and viscosity. They are flexible, then scale up friendly, however not suitable for large number of stages, right. You see, if you go on increasing the number of stages to 30, 40, then there will be 30 mixing tank, 30 settling tank, which is not possible, right. So, mixer settler can work 3, 4 up to this number of stages, and they have got very high stage efficiency, right. So, second one is unagitated columns. So, this may be a spray column. See, what is a spray column? We have this, here we have a port, a sparger, light liquid in, then light liquid out, heavy liquid in, and from the bottom heavy liquid out, right, and one of the phases will be dispersed in the other. So, this is the spray column. Similarly, we can go for packed column. And sieve tray column, column with sieve tray or tray column. So, here we charge this heavy liquid in, heavy liquid out, light liquid in, and from the top light liquid out. That is a plate column, sieve tray. Right. So, spray column, packed column or sieve plate we can use, and here it is low. What are the feature advantages? Low this maintenance, a low capital and operating cost. High height of the transfer unit and relatively lower mass transfer efficiency. Right. Now, in the same structure, we can increase the mass transfer efficiency if we go for pulsed column. This simply, you see, we can use a packed bed as well. A packed bed, the structure again it's same. Light liquid in, heavy liquid out. Here we have heavy liquid in and light liquid out. However, in this line we attach a pulsating cylinder, piston cylinder assembly. Right. So, this is the pulsation generating accessory, and we can increase the mass transfer, the high mass transfer coefficient we can increase. So, obviously it will be of low HTU, high mass transfer coefficient, no internal moving parts. Right. Next we have rotary agitated columns. I am simply drawing what is called the rotating, there are different variations, rotating disc contactor, RDC. What is that? We have a shaft protruding to the end of this column. Here we have a bearing. Here we have the motor and bevel gear arrangement, which will actually transmit the direction of motion. Additionally, there is a variable speed drive, right. So, there are plates fitted with it, which are rotors. Series of parallel plates over the entire assembly, and in between we have the donut shaped stator. So, here we charge the light liquid in, here we withdraw the heavy liquid, charging this heavy liquid and withdrawing light liquid, right. So, definitely this rotating disc contactor, they have got moderate to high capacity, accommodates many theoretical stages and low cost of operation. So, moderate to high efficiency, moderate to high capacity rather, low HTU and can accommodate many theoretical stages and low cost of operation. Relative to other columns like reciprocating or this centrifugal, right. So, 1, 2, 3 and 4. Next, let us again go carry forward this discussion and characterizations or characteristics. We have 5 reciprocating plate column. So, this is known as car column. It looks like there is an enlargement, I think, such that as we are increasing the volume. So, here we have a shaft and the shaft basically reciprocates. It is a piston rather, not a shaft. Right, and the plates are mounted, perforated plates. These are mounted between the circular supports like this. So, here we charge this light liquid, withdraw this heavy liquid and charge the heavy liquid here and withdraw the light liquid from the top. So, this entire assembly is with these perforated plates. They simply reciprocate inside the column. So, this leads to low HTU, much higher mass transfer coefficient. So, can handle emulsifying as well as solid particle containing liquids right, can go for high loading, flexible in operation, etc. Right. So that's about the reciprocating plate column. And the last one is this centrifugal extractor. It's a compact design and it can be actually mounted on a tabletop, used in mostly pharmaceutical industry for the extraction of penicillins or antibiotics, vitamins, etc. Centrifugal extractor. So its technical name is pod Belniak, or in short we call it pod extractor. So what happens here? We have a hollow shaft, right, but the shaft is partitioned into two with a solid plug in between, and over this we mount perforated cylindrical casings like this, multiple perforated cylindrical casing. Right. Multiple perforated cylindrical casing. Like this. So these are all perforated. Now the shaft also has an annular entry, an annular section like this. Now see what happens. Through the central core, and there is an annular region, through the central core we deliver heavy liquid in, and on the other side and outside definitely there is a solid case, right, there is a solid casing, that is the cover. So through this left hand side or right hand side we deliver through the central hollow region we deliver the heavy liquid, and here we deliver the light liquid. Okay. Now heavy liquid is released close to the central region. So heavy liquid out here, and light liquid we release near the peripheral region. Light liquid in, and here heavy liquid in. And light liquid we withdraw. If I admit the light liquid on the right hand side, we withdraw the light liquid through the annular region on the left hand side. Light liquid out. And here we withdraw it close to the central region, whereas the heavy liquid we withdraw again through the annular region somewhere here. Right. Why such arrangement? Because the heavy liquid, whenever we discharge it in the device close to that central region, because of its density, higher density, and this entire device rotates at a speed, right. So, basically the heavy liquid moves outward, displacing the light liquid which were released near the peripheral region. So, here the light liquid will accumulate, the heavy liquid will accumulate and try to move towards the peripheral region, displacing the light liquid which will move to the central region. So, that is why the outlet of the light liquid is in peripheral region, whereas the inlet of this light liquid is the peripheral region, whereas the outlet of this light liquid is through the central region, and just the opposite for this heavy liquid, right. And as we have perforations, we have a huge contact area being generated over a very short or over a very small volume, right. So, that is why the centrifugal extractor are highly compact in design. This compact requires small residence time, can handle low density difference system, and we have this can treat also emulsifying system. Right. So, based on this idea or descriptions, we have to select the appropriate extraction equipment for the given duty. So, that is the first task of the designer, that what is my size of that system, what is the capacity, whether we want high throughput, whether headroom is available, etc., etc. Based on that, we have to actually decide about the type of equipment. Next, you see that once we are discussing here about a system where we have a liquid-liquid dispersion. So, if I have a liquid-liquid dispersion, the drop size must be characterized. Okay? And generally, just like in size reduction, we choose this volume surface mean diameter to be the most appropriate statistical average. Here we choose shorter mean diameter. Representation of drop size for LLX, right. The shorter mean diameter is most appropriate. Right. So, here why the shorter mean diameter is appropriate? Here we have the volume is important because the volume determines the loading, and at the same time the surface is important. So, D32 is defined as Ni into Di cube divided by Ni into Di square. Let us say we have the number distribution like this for different groups. Right. So, we will consider the mean as Di, the respective number will be Ni, and from there, from this number distribution, a differential number distribution, we can actually determine the shorter mean diameter. Now, shorter mean diameter has got a direct relation with this interfacial area per unit volume, right. So, interfacial area per unit volume of the dispersion we can calculate, like say the total interfacial area for n is basically the summation of n into d32 square into pi, right. So, average we are reducing this heterogeneous distribution into an average, and that is the Sauter mean diameter. So, for individual average size drop, the surface area is pi d32 square, and that multiplied by n will give you the total surface area, and the volume is n into pi by 6 d32 cube. So, specific surface area is basically n into pi into d32 square, and now this is the volume of the dispersed space, right. This is the volume of the dispersed space. What will be the total volume? If the dispersed space has got a volume fraction phi, the total volume V, the total volume of the dispersion is Vd divided by phi, where phi is the volume fraction of dispersed space. So, it is n into pi by 6 into d3 cube divided by phi. So, it is going to give us 6 phi divided by d32, that is my equation. So, 6 pi divided by d32 is the Sauter mean diameters relation with the volume fraction and the interfacial area. Now, Sauter mean drop size can be calculated from these empirical correlations. I am not going to discuss about these empirical correlations, and there is something called minimum impeller speed, which can also be estimated from empirical correlation. What is the minimum impeller speed? The impeller speed at which we will get a stable liquid-liquid dispersion, right, with homogeneous property nearly. So, Sauter mean diameter and this minimum impeller speed we can calculate. And regarding the power consumption, okay, let me write, because you have to understand the structure of this empirical correlation. So, how to get the Sauter mean diameter? Empirical correlation, which is d32 divided by di, that is the impeller dia, and these relations are for this mixer settler. So, this is equal to 0.053 1 plus 4.22 Vi whole to the power 0.6 into Weber number to the power minus 0.6, where Vi is mu d Ni di divided by sigma, then rho c by rho d to the power half, then d32 by di to the power 1/3. Now, this We is Weber number, right. So, what is Weber number? See here, mu d stands for the dispersed space, c stands for the continuous phase, Ni is the rotational speed of this impeller, and di is the impeller diameter. So, this Weber number you see is inertial force by force due to interfacial tension. Right. So, inertial force is rho v square L square, where v and L are characteristic dimension of that system, and inertial this force due to surface tension is sigma into L. So, it is equal to rho v square L divided by sigma. So, for the specific system, right, where Weber number here we can define based on continuous phase as rho c. Now, V, see, for this system, V is in the order of Ni di. Why? Because pi into Ni into di is V, the tangential speed, that is a characteristic velocity. So, Ni di and here di square divided by sigma will be the expression of Weber number, right. Now, similarly, we have the minimum impeller speed. Here the point is not to remember this equation, but to understand the definition of Weber number, right. And this is most important, inertial force by force due to interfacial tension. Now, minimum impeller speed. So, for minimum impeller speed again, this is Fr m minimum. What is Fr m? Froude number for mixture, and that is equal to 1.03 into dt by di, dt by di 2.76 into phi, the volume fraction 0.106 into BO into GA to the power minus 0.089, right. So, this is the Bose-Einstein number right, yes. Bose-Einstein number, and this is Galileo number, right. Now, Bose-Einstein number, or first let us discuss the Froude number. Froude number is what? Inertial force by gravity force, right. So, it is rho v square L square rho L cube G, right, V square divided by Lg. Now, Froude number for mixture, here Froude number for mixture, how it is defined? Froude number for mixture, see, for this present system again V is Ni di and Ni square di square divided by di. So, it is Ni square di divided by G. Now, whenever we are transforming it for the mixture, we multiply it by rho mixture divided by the difference of density between continuous and the dispersed space, right. And similarly, we can also define Froude number for continuous phase Ni square into di divided by G. Froude number, that is Froude number for continuous phase. Now, Galileo number is very similar to this Archimedes number basically. Galileo number is bound force into inertial force by square of viscous force. Bound force, inertial force by viscous force square, right. Bound force is rho into L cube into G, or rather, yeah, the bound force is rho into L cube into G. Inertial force rho V square L square divided by mu V by L into L square whole square. So, it is becoming, see what it will become, this V square and V square cancels out. Here we have got L, so L square and L square cancels out. So, it is the Galileo number becomes in general rho square L cube G divided by mu square. So, for this present system, Galileo number is written as, say, characteristic dimension is diameter di cube, that is there. Then rho m, rho of the mixture into delta rho, which has got the dimension same as rho square, into G divided by mu m square, right. And similarly, we can define the Bose-Einstein number, what we have used for the minimum impeller speed, as bound force divided by force. So, Bose-Einstein number is equal to bound force divided by interfacial tension. So, bound force is rho into L cube into G divided by interfacial tension sigma into L. So, this is in the order of, so rho into L square into G divided by sigma. And for the present system, this Bose-Einstein number is defined as di square, then delta rho here, delta rho instead of actually this, whenever we are thinking of bound force, it is bound force minus the weight actually. So, that is why this rho should be replaced by delta rho. So, di square into delta rho into G divided by sigma. So, these are Bose-Einstein and Galileo number for the present case, right, and from there we get this minimum impeller speed. So, the rationale or objective of this discussion is not to actually discuss this empirical correlation. Empirical correlations are simply outcomes of experiment, but in this relation we want, or we actually I have actually planned to discuss about the different dimensionless groups involved in the physical characteristics of this liquid-liquid dispersion system. So, in terms of shorter mean diameter, we have got this Weber number. For minimum impeller speed, we have got this Froude number, we have got Bose-Einstein number, we have got Galileo number. And the last one, the physical characteristics related to it, is the power number, right. So, this is related to power consumption. So, actually for, we will discuss it in mechanical operation. For high turbulence, where Reynolds number is greater than 10 to the power 4, we have power number PO nearly equal to 5.5 independent of Reynolds number. Right. And a power number is defined as, so power number is defined as P divided by rho into n cube into L to the power 5, right. And its significance wise, it is same, or this is basically equal to drag coefficient. We have discussed it in fluid mechanics. It is basically equal to drag coefficient, and for the present system the power number will be P divided by rho into Ni cube into Di to the power 5. So, if I say that power number is equal to 5 or exactly 5.7, not 5.5, 5.7, this you can note and remember. We will also have certain implication in this agitation and mixing for this mechanical operation. So, there the power number actually flattens off, it attains a threshold, lower threshold for Reynolds number greater than 10 to the power 4. So, we have discussed about some physical characteristics, right, that is shorter mean diameter, minimum impeller speed, then power consumption, etc., in a specific baseline mixer-settler type of liquid-liquid extraction device. In the next session, we are going to just have a little discussion regarding the mass transfer properties, like how to find the dispersed phase and continuous phase mass transfer coefficient, and from there we will start about this discussing drying. Thank you.